So let us check a couple of examples on this concavity or on the second derivative test. So for the first example here, we have the function given by y equal to x cubed. So you see it's stated figure 4.24 there, okay, according to one of our textbook. So we need to decide whether the function concave down or concave upward, and if it is concave upward or concave down, in which interval does it happen. So it's pretty obvious, okay, from the figure here, but okay, no problem. We are going to ignore the figure that we have here for a while, and we'll see from our calculation or our differentiation, okay, what actually happens to our function. So we have our function here, y equal to x cubed. Okay, we need to check on our second derivative. Okay, so of course the first derivative is given by y equal to 3x squared, and y double prime is equal to 6x. So we already have y double prime stated here because we want to be able to make the conclusion only, and the process of finding the derivative is not that difficult. So the curve y equal to x cubed is concave down, right? So we have here, you can write it down on this interval negative infinity to 0, because here the second derivative, that is 6x, is less than 0, right? Because we have the values, okay, before 0 based on the interval, okay, the values that we are going to plug in here, the values of x is always negative, right? So we have the function 6x here, we plug in any negative value, okay, the function, the second derivative here will always be negative, and that is why we have the function to be concave downward on that particular interval. And of course, in contrary, we have it concave upward or concave up here on the interval 0 to infinity, where 6x is always greater than 0, based on the similar conclusion. You have 6x, you plug in any positive value, it will always be greater than 0. Okay, so we have another example here. Okay, the curve y equal to x squared. Okay, so we need to find y double prime as well. So the first one is y prime is equal to 2x. So y double prime is equal to 2. So you just differentiate this one and you get 2 here. And it happens that 2 is always positive, right? You can, okay, you cannot plug in any numbers lah, because you don't have any unknown here. You don't have x here. So 2 only. So it is always positive. And of course, if our second derivative is positive, then here we have it is always concave upward on negative infinity to infinity, okay, according to the function's domain. So because its second derivative is y double prime equal to 2, okay, it's also, you can state here, always positive. So you can choose any part of the function, and you will see that the second derivative will always give you positive value, that is 2, and you can make a conclusion that it is always concave upward. So now let us proceed with second one. The third one, even though it is stated 2 here. So determine the concavity of y equal to 3 plus sine x on this interval 0 until 2 pi. Okay, so the first derivative of y equal to 3 plus sine x, we have, okay, let me write here, we have y prime equal to cos x. Because we have two terms there, we differentiate 3, you will get 0, right? It is a constant. And if you differentiate sine x, you will have cos x. So y prime equal to cos x. And the second derivative is y double prime, and that is negative sine x. Alright, you just differentiate this cos x and we get negative sine x. So we know that from this fact, okay, of negative sine x, the graph of y equal to 3 plus sine x is concave down. So I'm going to use a symbol only because of the limitation of the space here. So it's concave down on 0 to pi, because we have negative sine x and our function is concave up on pi to 2 pi, because our y double prime or our negative sine x is positive. Okay, so if you are not certain about my conclusion, you can try to plug in values. Okay, first one maybe from 0 to 2 pi, 0 to pi. Okay, you plug in the values and you see that the values is always negative, and this is also actually reflected in this yellow lines here. So we plotted this yellow line for y double prime negative sine x. So you can see the values here from 0 to pi is always negative, and from pi to 2 pi it is always negative, and it is reflected in our original function y equal to 3 plus sine x, because here we have negative. So you can see the shape here, concave downward, and when y double prime is positive, is concave upward.